In this video, we're going to discuss inertial reference frames. The situation that I'm going to be using to illustrate inertial reference frames is used in Introduction to Electrodynamics. And if you took Physics 261 with me, we referenced this book quite a few times in Physics 261. This is one of my favorite physics textbooks, but unfortunately the math level is above what is required for Physics 261 and Physics 262. However, I don't think it makes too much of a difference for Physics 262 if you do want to refer to this book. For Chapter 12, Sections 12.1 and 12.2 are related to the material that we are going to be covering in this course. The math is at a higher level, so I think if you read through section 12.1 and 12.2, there'll be more covered in this book than what we are covering in our course. So if the math gets a little bit beyond your understanding, that would probably be a good place just to stop reading. So it's only part of one chapter, which is related to the material that we're covering in this course, but what is covered in this book I think is really good. So if you can find a copy of it, I think it would be worth looking over. Okay, so we're going to talk about inertial reference frames. And so in an inertial reference frame, it appears that Newton's three laws of motion are correct and they hold true in that reference frame. So suppose you are trying to play a game of pool and you are riding on a train. Do you have to play differently because of the fact that you are playing on a train? So if the train is traveling down a straight track and the track is smooth and level, then you shouldn't have to adjust anything to account for the fact that you are on a train. So all the laws of physics work the same way as they would if the train was at rest. However, if the train turns a corner, or if the train starts slowing down or speeding up, then you would have to adjust how you play the game or wait until the train finishes rounding the curve or speeding up or slowing down. So if the velocity is constant, then the laws of physics work the same way that they would if you were at rest relative to the surface of the Earth. However, if the train is accelerating, then the laws of physics appear, Newton's three laws at least, appear not to hold true. So a similar situation would be if you are driving in your car and you have a wedding cake on your front seat, and there's very little friction between the platter that the wedding cake is sitting on and your front seat. If you slow down very quickly, the wedding cake might continue to go forward. Relative to you, the wedding cake is moving, even though if you look at the wedding cake and analyze the forces, you would say there's no force causing the wedding cake to move forward. But this is because in order to correctly analyze the situation, you have to recognize that you are in an accelerating reference frame and the wedding cake is just continuing to move forward with a constant velocity because there are no forces acting on it in the horizontal direction, or a very small frictional force and not enough to keep it on the seat in front of you. Okay, so an inertial reference frame is one in which it appears that Newton's three laws of motion hold true. And in this section, we are going to be studying special relativity. And one way to define special relativity is that the laws of physics are the same in all inertial reference frames. So it's important for us to know what an inertial reference frame is. Okay, so we have special relativity, which can be defined as the laws of physics are the same in all inertial reference frames. And so to test whether or not we're an inertial reference frame, we can see whether Newton's three laws of motion would hold true. Another way to define an inertial reference frame is to say inertial reference frames move at a constant velocity relative to other inertial reference frames. This is kind of nice because if you want to know, like for instance, in the previous problem, which of these cars could be considered to be an inertial reference frame, you don't have to ask for each car, would Newton's 3 laws hold true in that reference frame? We can just say, well, if these cars are all traveling at a constant velocity, then they're all moving at a constant velocity relative to the Earth. So if the Earth is an inertial reference frame, then each of these cars would be an inertial reference frame also. So we are going to look at 2 inertial reference frames, and then we can compare everything else to one of these 2 inertial reference frames to see if that would be an inertial reference frame as well. So the first inertial reference frame would just be, let's say, the universe. So you have objects in the universe which may be moving, but just like if you're out in the far reaches of deep space in a spaceship and you're far away from any large objects that would be exerting a force of gravity which isn't negligible on your spaceship, and if your spaceship isn't, like the engine's not running, it's just out there floating in space, that would be an inertial reference frame. The other inertial reference frame which we're going to consider is Earth itself. However, we know that inertial reference frames move at a constant velocity relative to other inertial reference frames. So if you have your spaceship out here, which is just sitting there, not doing anything, really far away from all large massive objects, and then you have the Earth over here, is the Earth moving at a constant velocity relative to the spaceship? No, it is not moving at a constant velocity relative to the spaceship. So it might be true that the sun is moving at a constant velocity relative to your spaceship, but we know that the Earth is rotating around the sun, and so the relative velocity between the spaceship and the Earth should not be constant. However, if you were to perform an experiment on the Earth, you would have to perform a very, very precise experiment in order to figure out that the Earth is not an inertial reference frame. And there is an example of such an experiment, and I'll send you a link to that if I can find it. But the experiment also has to take place over a very large distance, so over the entire United States, going from north to south. So the Earth is an approximate inertial reference frame. So we're going to treat the Earth as an inertial reference frame. So I'm going to list out some inertial reference frames, and I'm going to list out some reference frames, and we're going to go through them and see whether or not we should consider them to be inertial reference frames. Okay, so we're going to go through this list together and determine whether or not each item on this list can be treated as an inertial reference frame. So we already talked about a spaceship floating in the far reaches of deep space and said that was an inertial reference frame. And if you have another spaceship which is moving at a constant velocity relative to the first spaceship, that would be an inertial reference frame also. But if the second spaceship was accelerating relative to the first spaceship, that would not be an inertial reference frame because we need to have a constant velocity relative to another inertial reference frame. And the Earth, we said, can be treated as an inertial reference frame, even though it isn't a true inertial reference frame. But it's nice for us that we're going to treat it as an inertial reference frame because a lot of the reference frames we look at are moving at a constant velocity relative to the Earth. And if we were able to use Newton's 3 laws in Physics 161 and not realize that the Earth was not an inertial reference frame, we shouldn't have to worry about it. Well, in this class we will have to worry about things that we didn't have to worry about in Physics 161. But we can treat the Earth as an inertial reference frame. Okay, if you have an elevator going at a constant speed, that would be at a constant speed relative to the surface of the Earth, so that would be an inertial reference frame. If you have an elevator in free fall, or an elevator which is speeding up or slowing down, you are going to notice that things are different. If the elevator is speeding up or slowing down, you will feel either lighter or heavier. And we're going to talk about an elevator in free fall later on in this course. So if the elevator is speeding up or slowing down, you're going to feel that your weight is different. If you're standing on a bathroom scale, the bathroom scale would measure something that's not your actual weight. If the elevator is speeding up or slowing down. If the elevator is in free fall, it's going to appear like Newton's 3 laws do not hold. So something we're going to look at later on in this course. So you're in an elevator, and unfortunately the cable in the elevator has broken, and now the elevator is in free fall and accelerating downwards with an acceleration of little g. But you decide to take this opportunity to perform some physics experiments. So you have a bag of oranges with you, and you pull out an orange and you reach out your hand and you let go of the orange. There it is. To someone outside the elevator, they would look at the orange and they would say there's a force of gravity acting on the orange. So that's not the force though, this is just the acceleration. So the orange should be accelerating downward with an acceleration of little g. However, the whole elevator is accelerating downward with an acceleration of little g. So because everything's accelerating downwards together, the orange is going to stay the same distance from the floor. And if you get hungry later on, you can just reach out your hand and the orange is right where you left it. So we're going to come back to this later, but an elevator in free fall or an elevator that's speeding up or slowing down is not an inertial reference frame. If a car is going at a constant speed on a straight level road, is this an inertial reference frame? Yes, if it's going on a straight level road at a constant speed, it is therefore going at a constant velocity relative to the surface of the Earth and is an inertial reference frame. If the car is going at a constant speed, but in a circle, is this an inertial reference frame? Well, you can ask yourself if it's moving at a constant velocity relative to the surface of the Earth, or you can ask yourself, if you're going around in a circle in a car, even though you're going at a constant velocity, when you turn a corner and you feel like you're thrown to the side of the car, it's not because your speed is changing, although your speed may be changing when you do that, but it's because the direction is changing. So even if you're going at a constant speed, because you're going in a circle, you would still have acceleration pointed in towards the center of the circle. Therefore, going in a circle at a constant speed is not constant velocity because you have acceleration when you're going in a circle. Okay, so that's not an inertial reference frame. If you have a car rolling down a hill, so this one you would need a little more information. I think rolling down a hill, by that I just mean that maybe we shouldn't make it a car. Maybe we should make it like a wagon rolling down the hill. That'd be easier. Because a wagon rolling down a hill, like if you just let go of it and it rolls down the hill, it would be speeding up as it goes down the hill, so that would not be constant velocity. But if your car's going down the hill at a constant speed, so you're like applying the brake to keep the speed constant and doing a perfect job of it, that would be constant velocity relative to the surface of the Earth. Okay, here, if we have a train on level tracks going straight at a constant speed, that was what we started off talking about, that would be an inertial reference frame. Can you take any one of these away and still have an inertial reference frame? So if the track wasn't straight, then it would not be an inertial reference frame, because whenever you go around a curve, you have acceleration pointing in towards the center of the curve. So it has to be straight. If it wasn't a constant speed, yeah, that wouldn't be a constant velocity. So the speed does have to be constant. You can't be speeding up or slowing down. So we talked about those when we began the video, talking about playing pool in a train. So you can't be speeding up or slowing down. The pool balls would roll either towards the front of the train or towards the back of the train if it was speeding up or slowing down. And if the track wasn't straight and you're rounding the corners, the pool balls would roll off to the side of the one or other side of the table. And if the track wasn't level, then you'd be accelerating but in the vertical direction. So if you're going over bumps, of course, the pool balls are going to be bouncing around. So it has to be a level track, and it has to be straight, and it has to be a constant speed for it to be an inertial reference frame. Is a rocket during launch an inertial reference frame? No. When the rocket is being launched, it's accelerating. And so you're going to have large acceleration during launch time. This would be like if you're speeding up really fast in like a jet plane or a rocket, you're going to feel like you're pulled downward. So you're going to, like, this is kind of like when you're in the elevator too, you're going to feel heavier than you really are when the rocket is speeding up. It also happens if you're in a plane and going around in circles, like not a commercial plane where, you know, you might just be doing circles above the airport, but like a pilot in a plane going in vertical circles like that really fast would experience large forces. Okay, a roller coaster going over a hill, that would not be constant velocity. So if you're going over a hill like this, that's kind of like going around a turn. So your direction is changing. Even if your speed is staying the same, if the direction is changing, remember velocity includes speed and direction. So if direction is changing, it's not constant velocity. A skydiver at terminal velocity would be in an inertial reference frame, because the speed is constant relative to the surface of the Earth.